So welcome to the uvwasi team meeting for March 13th, 2024. We took an initial look at the agenda, so I think we've agreed that what we're going to do is really just look at or just go over a topic which Guy is going to take us through. So at that point, I'll just hand it over to you, Guy.
Thanks, Michael. Yeah, so the topic that I was suggesting today is particularly for the preview to and the the next sort of version of WASI and the current host bindings story there. So the project that I maintain, Jco, is a WASI preview to a project that can support Preview 2 on top of existing core WASM today. So it rewrites WebAssembly components that use WASI bindings into JavaScript and core WebAssembly modules. Sort of we say transpile, and that code can then run in Node.js today. And the current bindings are very much like WASI Preview 1. They extend the sort of standard POSIX style bindings, and then that'll grow over time to support other things. There's a whole bunch of different APIs in WASI that are looking at being supported. And so I can kind of maybe just share my screen and show the way that binds today to Node.js and how we support that on top of Node.js. And then the topic that I want to get to, if we can get the groundwork in on that, is what optimized bindgen would look like for this. And this is actually something that I just got a first prototype of last week. And it's I guess a low-level version of the same bindgen that can fit into the same scheme. And so it's quite interesting. But understanding it it's like quite a complex area. So like understanding how it fits into the picture, it involves sort of understanding where things are with the high-level bindgen first. So maybe we can just look briefly at the high-level bindgen, what that enables and how that works in, and then I'll go through the low-level bindgen document briefly. And the main point is just to outline that like we've now proven an approach that works. I've actually shipped it, and it's comprehensive in terms of how the low-level bindgen is defined. But yeah, I'll get to that. So yeah, let's start with the current story. So when you write a component, you're going to be binding against file system APIs, whatever POSIX APIs, clocks or whatever, and that's implemented in this Preview 2 shim project, which at the moment is like a npm package you can install. You can install bytecode alliance Preview 2 shim, and you'll install this this package here, which has a Node.js implementation of these WASI APIs. So you can sort of do import bytecode alliance Preview 2 shim /CLI, and you'll get the CLI package. And we've got browser and Node.js versions. The browser version is experimental. The Node.js version is actually now fully supported, so it's fully conformant against all the Preview 2 tests. And when you import this API, what you get is a translation of the WIT APIs. And so we've got this WIT language. So if you look at it like the WIT for file system, the file system types are defined as an interface, and just like a descriptor type is an enum, descriptor flags is a flags, all the different types here. And then on the actual file descriptor is called a resource. And on the resource, you have functions like read via stream for streaming reads, write via stream for streaming writes. And you've got all your standard FS operations, which native code can link to, but using kind of this high-level engine. You've got a direct read function, write, stat, all your standard file system operations. And these are operations for like methods on the resource. And so the descriptor already exists. you call descriptor.stat and you get something. So like this is it's a very it's a low level language, but it's a high level bindings, right? So it's a low level subsystem, but it's high level bindings. So when I use this in Node.js, I can just go like import you actually to get a descriptor in the first place, it has to be a pre-open. And so traditionally pre-opens were like originally set up in preview one, they're pre-initialized. In preview two, you have to do something similar. You have to call a get directories function, and you'll call get directories from the sort of WASI. I think it's which one is it? It's CLI. It's not CLI. Which one is it? Is it file system? Yeah, pre-opens get directories. So you'll do import pre-opens from WASI file system, and you can do pre-opens.get directories. And that'll get you your pre-opens. And then you can look up a descriptor in there. It'll be all the pre-open directories. So it'll be sort of key value. I believe we can, again, check the width to see what it is. So get directory is going to return a list of tuples of descriptor and string, which is the path of that. So it's going to be pre-opens is going to be a list, and then you can do sort of for, and it's going to be a tuple of descriptor and string and path, and that way you can iterate your pre-opens. So I can I can immediately translate to high-level JavaScript how I'm going to be accessing these objects. So low-level bind gen. This is like the core API. You can think of it similar to like Node APIs. It's the core system API. And then this descriptor is going to be the resource, this resource descriptor, which is going to be represented as a class in the high-level bind gen. And so it's going to be a class in JavaScript. And so if I've got one of these descriptors and I want to do a stat on it, I can do descriptor.stat, and I'll get back the stats on that. And then if we look at how stat is defined, it's going to return a result, so my error, and it's going to return a descriptor stat. And a descriptor stat is going to be a record. So in JavaScript, it's an object, and it's going to have these things on it. So I can say stats.size is then going to be the size of that file, and that's going to be a file size. And if you look here, file size is just a U64. So, and that's going to be in JavaScript, it's going to be a big int because U64 is bigger than JavaScript numbers allow as in integer ranges. So I can
Quick
log
question.
Yeah.
Is it fair to assume that there's a generator that takes the WIT and generates JavaScript like stubs effectively that you can then implement? Is that what you did, or did you have to do it all by hand, I guess is
yeah, so I guess there's two sides to the story, right? So you've got, on the one hand, you have like, because I'm consuming the WASI host API here, I'm consuming a high-level API that was pre-created. And this preview 2 shim project is an implementation of this API. So when I do all of this high-level stuff,
yeah.
I'm actually directly using these implementations that we've written that match the conventions. Now, yeah, I wrote all of this by hand.
Okay, that was my question. Like, is there a generic, like, I got a
Right.
WIT, it gives me some
So
JavaScript, because that seems really like we'd
yeah.
want that.
So code gen is like the code gen story is well defined. There aren't a lot of code generators. Like in theory, because the rules are well defined, you could take a WIT and you could
Okay.
just code gen the shape of all the functions you need to define and fill them in with to-dos like that. But that is not yet kind of
Okay, that doesn't exist. That was basically my question. Does
it's
that
definitely something we
automatic?
need. It's
Yeah.
definitely
Okay.
something we need. Yeah, no one's working on it currently, but that's
Okay.
definitely sort of part of the story is you can get easy setup. And we do have type generation, so the type's automatically generated. So if you look at file system, and maybe this is the kind of intermediate step, that this is automatically generated types from the WIT. And so you can see the types of things where this is this interface, and then you can see the WASI file system pre-opens, and it's got even the comments from the WIT get turned into .comments in the TypeScript. And you've got, descriptors represented as an actual class, and it's got all its methods on it. I don't know why the comments aren't coming through. That's an issue we need to fix. We should be proper code help in that. But this is all automatically generated from jQuery's type generation. So jQuery has a types generation mode for WIT where you can just spit out the types for.
Okay, so it's the answer is some of it, like the types part, yes, but the actual functions that make those
code
types
boilerplate,
yeah.
no. Yeah.
Yeah, okay.
So all of this to say that you can sort of see like implementing kind of a host API, but you're using it in a high level way. And so when I take a component, so like as an example, here I've got a component called wasmtools.component, which is jQuery's internal bindings to wasm tools, which it uses internally to sort of self-host. And the width for that is here. So it's got a tools and it's got things like parsing WASM, where you can pass in a string and get out a binary. Printing WASM, you can pass a binary and get out a string, and various other like helper functions for WASM operations. As an example, components, if I jQuery transpile that, so I do jQuery transpile WASM tools, dot component, and I output that to WASM tools. It's going to take that component, which is a full implementation, it's a Rust implementation of how to do all that stuff, and it's going to turn it into a JavaScript file that I can import. So I can go WASM tools equals await import WASM tools dot component.js that is just transpiled. And if we look at WASM tools, we've got all of those operations here where I have the pass and the print using the same WIT definitions and the same bindgen definitions. So I can say WASM.
So is that generating an interface to the WASM?
So
like the WASM thing, or is it replacing it with a complete transpilation?
Yeah, so this component is a fully self-defined component that I've got existing. I'm using WASM tools because it's one I just have lying around. And so when you transpile it, it fully converts the whole thing, all of these files. It does the types, so you can see the types when you import it, and it's got some WASM files here, and it's got a JS file here that represents when I import it, it looks the same as this component basically, and behaves.
What I'm trying to understand is it giving you the front end to access and run things in that WASM, or is it like converting that WASM file into something that's completely JavaScript that you then run?
The component model it's like a higher level type of WASM, like a WASM. Because it's a component WASM. A component is like normal WASM is low level, and then a component is like high level, and it can have embedded core WASMs inside of it, and it can have a bunch of bindgen around it as well. And so it encapsulates the whole story. That's why you can get all the way to the sort of high level bindgen here when I was able to. So
it's still not quite understood.
Yeah.
Like what I'm trying to understand is that WASM, when I run, do I still use that WASM file, or is it like
the WASM tools.component.wasm I'm no longer using. It's been converted. It's been converted into, but inside of it, it's got core WASM binaries, because a component WASM, if I do, what's a good way to do? I forget what the function is to get a really nice breakdown of what's in a binary. WASM tools. Is it meta? Which is the good one for this? Dump? Yeah. Object WASM tool. So if you look at this component, that's not what I meant. Just the one that gives the kind of outline of it.
I think it might be component WIT. or something. I think it's a
Yeah, component
subcommand of
width will
component.
give the width interface. So yeah, WASM tools component width for this WASM tools dot component will give the sort of the width definition of it, where it's exporting this tools interface, importing from WASI preview 2. But I forget, there's one that like shows you the sections, just like the sections in the binary.
Yeah.
So maybe I'll play this back again. What I think you're saying is like this component WASM is a wrapper around a bunch of other WASM
Yeah.
binaries.
Yep.
Like a WASM
So
bundle
the,
thing. Yeah.
the
Yeah, it's a
wrapper
bundle.
thing has been completely converted basically to like JavaScript.
And the inner
But
core WASMs are just pulled out. Yeah.
there still WASM. So like, if I've compiled my Go code to WASM, that compiled WASM is still being run.
Yeah.
Versus like the whole. I was just trying to understand, like, has everything been converted to transpiled,
No,
or
so just the wrapper code. So
okay,
all of the glue code, it becomes
right,
JS.
okay,
And then you've still got like, here's one WASM, here's another WASM, and they've been extracted. Like, so inside of that component, it could have any number of core WASMs, and they
right.
get extracted out. And there's various composition rules and instantiation rules and bindgen rules, and sort of it's all of the like, it's like a glue wiring language. So it's like, how do you link together imports and exports, and what do you expose and what do you link to what, and then you get the final kind of thing.
But those WASM files are still loaded and run by V8.
Exactly.
Yes.
So
Yeah.
there's
Okay.
so here's the glue that it's got, and this is the full thing. And internally, it has this initialization function that'll go and take those core WASMs, and then it's wiring them up and individually instantiating them and binding their imports. And at the
Right.
end,
Okay.
it's giving you back this tools export, which is the final sort of exports from one of these modules exports. Okay, yeah. So like
Okay.
when you call components, when I call pass, for example, on the exporter interface has this pass function, and that pass function will come from here, where I'm passing in a high level string. It's then doing the UTF encoding, and then it's going down and calling the low level call function. Sorry, with the low level like pointer and length to that string that it's encoded. And then this is coming from exports 1, which is created here as part of an instantiation of one of as that first call module. So it's instantiating this component, and then it's calling it with the low level functions, and it's encoding the strings and handling the sort of memory management and things like that, and then pushing through the sort of WASI interfaces. And the WASI interfaces, so finally getting to the high level bindgen. It's good we could go through the background, because I think I want it to be clear like what high level bindgen is and how it fits into the story. So when this does file system operations, it's going to call the file system operations using these preview 2 bindings. And the way it gets those is it imports from the preview 2 shim project. So when you're running on Node, all of the low level operations are pushing down to these imports. So I've got my pre-opens and my types being imported here from my file system. And so when I do something that uses file system, like get directories, it's being called inside of these trampoline functions that are actually doing the converse of what we just saw in that pass function, where the pass function is what you call like a lowering function, because it'll take the high level APIs, lower them down to low level, and call the low level functions. Whereas this trampoline that's been generated is a trampoline that calls a high level API for get directories. And this is actually a lifting function, because you are the trampoline here is a low level function that internally is then calling a high level function, getting a high level return, lowering that high level return back down to a low level data that can be passed back to the low level call as a function.
You're calling from WASM to JavaScript effectively.
And when you do it, but then it's going back through JavaScript, and then so you call get directories, and then you're hitting this very high-level get directories function, right, which is returning a JavaScript array with the pre-open entries, or these JavaScript classes. So if you're doing something on a resource, if I'm doing there should be a file read here somewhere. Let's see what we've got on descriptor. Read. Yeah, so like here's a read directory entry, which is RSC0. So this is a trampoline. It's one of those low-level functions. And that low-level function is going to be called, it's going to say, well, against descriptor 5, read the directory entry on descriptor 5. And that'll come in as this arg0, which will be a handle to a descriptor. That handle gets looked up in the handle table. And what we get back from that is now a JavaScript number, which identifies, we give each of the descriptor classes here, whenever we have a descriptor instance, we assign it a number, which is called a representation number, a rep. We get that rep and we look it up in this kind of capture table. And so this object RSC0 is actually going to be a high-level directory entry stream class, which is going to be this directory entries. It's going to be an instance of this high-level JavaScript class. So you've got this like very low-level code manipulating high-level JavaScript classes. And like from a virtualization perspective, it means you can have it calling, you can define JavaScript APIs and have WASM calling them using these same conventions. So I mean, this is all the sort of bindgen, and it's a lot of like, low-level bindgen rules. But at the end of the day, it's just calling a method on the class. And this is the read directory function. And then this trampoline 22 is going to bind into 11 in something here, and it's going to bind to something else, which will eventually come out as the representation of this read directory method that's being passed into the WASM instantiation of one of these WASM modules. So it just calls read directory and says, read the directory with this handle, this method, or this arguments and low-level numberings. Meanwhile, it's calling this high-level thing. All that to say, this is hopefully motivating why low-level bindgen is an important thing. So it's all well and good that we can call high-level interfaces from WASM, and that's an important use case. And that we can import a low-level interface like WASI and have high-level APIs to work with it. I can directly import. I mean, to give you an example of one of these APIs, I can import bytecode alliance, preview to shim random, for example, and I can get my random API. And on random, I've got random.get random bytes, which I believe just takes a big int of the number of bytes to get. Yeah. And it'll return me some random bytes. So that's a high-level interface that I can call. But really, if you think of all the bindgen that's going on here, we want there to be an optimized bindgen path, both for when I create my own APIs. So like, maybe I'm writing the preview2 API, and I'm running it in a lot of places that don't support the native API, so I have to just use it in a high-level way. But maybe there's environments where we can have better, and obviously as we think about uvwasi, we need to be thinking about what's the low-level representation of this stuff in the C code that it's going to represent the preview2 APIs.
Because right now it's basically WASM to JavaScript,
yes,
potentially back to C, right? Like where, because it's, a lot of the actual file access, for example, in Node is in C. So it's like going across multiple of those layers, each of which I'm sure costs,
so we need
right?
to flatten that layer. So when you lift and you lower again, you can replace that with just not doing any of the lifting and lowering, and you go straight from A to B. You need the contract for that, and so in the component model, there's core ABI for everything, which kind of defines what the low-level functions are for all the high-level bindgen functions. So for every high-level function, it's a well-defined low-level WASM function signature. So I can give you any width function, and using component model spec, say this is the low-level representation of that function. But
Doesn't
that,
there always have to remain at least one lifting and lowering? Like, I don't know if that's the right terminology, but like you have to get from WASM into something and then from something back into WASM, like in terms of the return values and everything. So
right.
we'd still need to go from WASM to say C back to.
Yeah, so we've got, like the imports in WASM, you can pass a JS function or you can pass a up to like WASM will optimize native function bindings. So if you've got a function that's like defined as a C function, it should be able to wrap that and unwrap it and treat it as like just a raw native function because it knows the signature. So there should be that kind of optimization in the engine that we should be able to plug into. So I think it's similar to fast calls for V8 or something like that, like this kind of direct WASM binding. But yeah, that's where you want to get to, is the direct binding story.
In a perfect world, if every JavaScript method was just a pure wrapper on a C function,
Right, exactly.
you could just basically say, okay, call this thing instead, but
Yeah.
I'm sure it's much more complicated.
So yeah, that is, and so the problem that I'm solving for Jaco is that we don't have uvwasi supporting U2. If we did, we could just do like some kind of like import directly from like node.wasi random or something. We can get our function that would have this kind of thing on it or something, or we could have some kind of way to instantiate directly to the low-level engine and pass in components. So instead of me transpiling it, have the component bound for me to the low-level interfaces that are available, and instead of Jaco having to kind of marshal it. But the Jaco problem I have is that like this is like we want these high-level bindings because it should be possible to use Preview 2 in a high-level way. Like I as a JavaScript developer, I can just import these APIs and use them. If I want to use WASI random in JavaScript, that's fine. But when you're taking native apps and running them in Node.js, we want to really optimize that binding as fast as possible. And given the constraint that we don't have anything in Node.js today, the thing was like, what's the simplest thing we can do to just optimize this binding? And my hope is that this does pave a cow path for the sort of patterns that are going to emerge as we think about what Preview 2 support looks in Node. And even at a basic level, what signatures we need to be thinking about, and the overall patterns that are emerging, I think can become the start of like what a Preview 2 binding convention would look like. So let's start with this get random bytes example as a basic one. Here it is as its trampoline, and you've got a bunch of wrapper code that's having to then get the random bytes as a JavaScript buffer, and then re-encode that into the WebAssembly memory, and then note that it's a return value. So you got this generated code. This is your lowering, and then on the other side, we've got the lifting, which is the actual get random bytes here. So admittedly, we're just directly returning random bytes from Node Crypto, but yeah, we're binding to Node Crypto, and so there's a bunch of wrapping going on. Also, there's a memory copy because I'm having to realloc the random bytes into WASM memory and then do a uint array set to copy that memory from the memory that was returned by the first function and then put it into the second one. So here's the low-level bindgen version using this new technique. So it's basically like we have this symbol on the high-level function called cabby lower. And if a function has this symbol, it'll take some various options. It'll take the memory and the realloc function. So it can sort of assign, it can create memory allocations inside of the WebAssembly memory. So it's a binding convention. So you first pass the bindings, and what gets returned from the function is a low-level function. And this low-level function is the low-level one that's only going to take U32s, U64s, F32s, F64s as arguments and return values. And internally, it's just going to be doing very low level operations. So there's no like object allocations, GC brushes. It's going to minimize that as much as possible. And so a lot of what's happening here is very similar to what was happening in here. So it's basically moved a lot of this code down a level. And instead of returning the high level buffer, it's putting it directly into a return pointer position. So it's actually like putting the pointer into its ret pointer place, putting the length into the ret pointer place. And when it, instead of using random bytes, it can now use random fill sync and pass a pointer directly into that WASM memory. So that nodes random fill sync is able to directly put the random data into the WebAssembly memory without us needing that intermediate copy anymore. So we're
Is
actually
this
pulling
possible on Node because there's extra methods like that random fill sync is a very Node.
exactly. It exists
Right,
in
okay.
Node crypto. Yeah.
Right, whereas the other one is you're just using
Random bytes, which returns the buffer. It allocates a new buffer and returns it to you.
and that's a standard JavaScript API.
These are both Node crypto APIs, which are yeah.
Right, so that's not going to run in the
No,
browser.
this is Node.js specific. So yeah,
I'm trying to understand why you couldn't just take the code in the new one you have and paste it into the other one instead of having it on a symbol.
because this is a high level function like I called it here. And when I called it, I got the buffer directly back. So as a JavaScript developer, I can also call this thing.
Is that okay? That's true, but like, is that needed to support WASM?
It's not, but the concept is that yes, this is a low level WASI API and most users won't need to import it directly. But other WASI APIs like HTTP, things like that, it does start to become things that developers can use directly. And so the point is that you can always use these things as high-level APIs or low-level APIs. And the distinction is down to where you sit in the software layering. And there's also virtualization benefits to that like as a JavaScript developer, I can write an implementation of random and a virtual implementation and sub it in.
I guess
Yeah.
maybe I didn't answer. Like, you're just calling random bytes and doing nothing else. I still don't understand why that implementation couldn't just be inside. Like, why can't it just be inside of the original method?
So you mean basically like this?
Yeah.
So then when I did it here, if I go here, I don't have memory. So as a JavaScript developer, I can't use it anymore.
So it's because like this.
So that implementation requires a WebAssembly module to be instantiated, right? I think what Guy's saying is that you shouldn't need to instantiate the WebAssembly module to be able to call these functions to get, I don't know, whether you're using it as for scripting or you're just using it in the REPL or whatever to see what the results are. You shouldn't have to instantiate a WebAssembly module, which is what you have to have access to memory and realloc.
Okay.
So I guess the point is that Jaco is a bindgen generator. You can have high-level components and low-level components, and yes, get random is something you probably won't call from JavaScript. But other high-level components like HTTP or WASI-NN, you're going to want to call these things from JavaScript. So we have a bindgen generator that can support both the high-level and the low-level. And we do have actually a mode for Jaco now. So the way I've implemented this in Jaco is if you looked at my WASM tools component that I did the transpile with, what I can do instead, let me just get my help open here. So I can add a import bindings mode, and I can say hybrid. And when I do that, this trampoline 30 is now going to have some extra code where if that symbol that lowering symbol is defined, it's going to go through that bindgen technique, and it's going to now replace trampoline 30 with that version, that low level implementation we wrote. So it's going to now be running on optimized bindgen, this WASM tools component I wrote. But if that symbol didn't exist, it could still use the high level version. So you could sort of get to a place where you can, like, maybe some hosts have the optimized version, maybe some hosts don't have the optimized version, they can still call the high version. But to get to your question, there's another mode which is like optimized only, I think I call that, direct optimized. And when you do that, yes, the assumption is that like trampoline 30 is only going to be, what was it, trampoline, remind me what the trampoline number was, 28 or 30, what was it? So where it's going to be directly using those, let's just get the latest version. And that's a bug. Okay. Yeah, I haven't tested this, as you can see. Where it directly uses those versions of the function. So it's actually going to directly call those things, as opposed to, so you can write it directly. So yeah, I need to test that. That would help. But yeah, so a version where you can write it directly like that. So you can bind to the different bindgens. The point is, as a tool, like, you're going to be generating high level interfaces, and they're going to be interfacing with each other. And so these conventions are kind of important. And what we get as a result is we get the Preview Shim project allows us to make available all WASI interfaces as direct high-level JavaScript interfaces, while also allowing them to be optimized using the low-level bindgen rules.
Right.
At the moment, I've just, yeah.
I think it's important to be able to switch between those various things. Like, I think what Michael is saying is, why do we need both of them? But I think what you just demonstrated, where you can generate the various types, is the more important part, right? Because a good example, of course, this is for Node.js, so you don't have the problem. But in the browser, if you were generating WASM with these imports in the browser, you can't necessarily share a memory between different WASM instances. So you wouldn't necessarily be able to write into that memory unless you set specific CSP headers, right? So in that case, you might want to do the JS. You might want to do the JS bindings and then do that full copy from the buffer, so that you're not writing directly into that memory between the two WASM instances.
Yeah,
so there's
low level bindgen should be the go-to for low level interfaces when you have it available.
Yes. Yeah.
But WASI is still a high level interface, so we should make it available to JavaScript users who aren't just binding to it. You can, like, you don't only use your FS APIs through a component that imports FS from WebAssembly. JavaScript users can also use it, and so we're catering to both user bases.
So if we look at that optimized method for a second, so this is still like all within the code that Jco generates.
Yeah, so this is the code that I've handwritten to implement WASI Preview 2 on top of Node.js.
Yeah, but I'm trying to like understand these. So you've got the optimize function that's still written in JavaScript. It's just written in a way that I think Blaine, understand, assumes a few more things. Like it assumes that
the call that's the point, is it should be, yeah. We should get to a place where we have a similar convention for WASI implement source of Preview 2 support in Node, where we have the high level and then we have this kind of way to do the low level. And however we do it, it can be done through this kind of symbol mechanism, or you wrap the instantiation process and say, don't use WebAssembly.instantiate. Use the special component instantiation, which will just bind everything for you.
And would I guess like in one, an easy thing is like, this is just the JavaScript function, right? So like one step would be a JavaScript run function written in C, which might be slightly more optimized. Although that still means that we're translating to JavaScript and then JavaScript to C, because like that function is going to be like, hey, I need to support JavaScript. And so we still haven't really removed the we're in WASM, go to JavaScript, go to C.
The shape of this function is something that can be implemented in C, basically. So like the thing that you would want in C would do exactly the same thing that this function does. Like that's what you would want the optimized native code to be doing.
I'm just thinking that it's not, we haven't gotten rid of the WASM to JavaScript to C translation. We've maybe made it run in native code, but
we've cut out the need to rely on. So it's the first stage where we've cut out, like, so you've got lift and lower. Before we had class instances and we're relating them, so the other thing is that when you've got a class instance, it's actually a resource table. And so another part of this bindgen is resource table sharing. And resource tables are a slab data structure which maps a resource table and a resource table index into a resource representation and the type of handle that it is, whether it's an own handle or a borrow handle. And so if you've got these like resource handles, and if you want to read more about it, I've got on the Jco project, let me just get this. It should be in the doc somewhere here. I haven't put it in the table of contents. But yeah, in the docs, optimized host bindings describes the scheme. And just the complex part is how resources are managed across the host. And the data structures that we use for that. So there's this ability to assign resource instances, representation IDs, handle resource deconstructor calls, and then here's the actual like main lowering scheme. And yes, all of this is only necessary because we don't have Node Core support for this optimization. So this is how we can build the scheme in for Jco. It's a first step, but the underlying semantics are semantics that can evolve into what Preview 2 should be thinking about how it should be working. So I think a lot of the outline, when you look at these functions and you see how it's taking a memory and a realloc binding and thinking about resource table allocation, all of the semantics and structure here is a template for how we want to implement Preview 2 in Node. And so these functions are basically, they have the ABI that's called the canonical ABI in the component model, where this is exactly the same function signature as the low level functions in the component model. And therefore represents the same low level C bindings that you would want in the native code to be written. So it's, yeah, a cow path. Solving a problem we had today, which was optimizing our high-level bindings. If we really want to finish this optimization job, it's a huge job to go through every API and rewrite it in low-level bindgen. But it's a comprehensive proof of concept. Well, down to that direct bindgen still needing some testing. Yeah, resources are a little bit complex, unfortunately. But getting resources fully handled here was one of the major kind of cases as well.
So, and this is what you're implementing in Jco itself, not like the proposal for how you would do it in Node, right? Yeah, it's just the Jco side. Yeah, okay. Got it.
It's a first step. Cool.
Because
Any of
even like those shared handles, that sounds like an interesting thing if you're gonna have half of them, like if half of them were managed by the lower level node implementation, half were managed outside, it's like that starts to even start to sound even more complicated.
Yeah, so if you're interested, I'll share a link to the optimized host findings. It discusses that problem, and that's one of the that was actually the bulk of the work was solving that problem. And just to give a rough overview, resources are like classes, and every component is its own isolated like island. So a resource always has a component that defines that resource, but any other components are able to refer to that resource and even construct that resource. And so the way resource tables work is for every resource, it has a home component that defined it. But when you're dealing with a handle to that resource, you have handle tables, and every single component has a handle table for every single resource. And so you have a handle table. If I have a reference to your resource, I'm going to have a handle table just for your resource, and I'm going to have those handles. And if you have a handle table for your own resource, you're going to have another handle table. And if I pass my handle to your resource to you, you're going to have to create a handle in your handle table to from my handle to your handle. So you kind of interchanging handles at each call site.
Right, like the component B's handle is going to just be a wrapper around that somehow says, well, this actually comes from this other component.
The handles actually move. So like I'm going to say I've got a handle to this resource, and it's more like Rust model. It's like borrows and owns. So I've got an own handle, and I'm going to give you my own handle. So I'm going to remove it from my handle table, and you're going to put it into your handle table. And then the underlying resource is a representation, which is the actual like pointer to the actual thing. And so that it's an own handle, or if I give you a borrow handle, you're going to create an entry in your handle table that's a borrow that you're going to drop by the end of the call.
But to use that handle, you still need to go back to the other like I can pass it to a method in the other component.
If I
Like,
pass it, I'm creating a new handle in that other component's handle table. There, it's a borrow handle that's pointing to the actual resource pointer. So there's an indirection through the handle.
okay, I guess what I'm trying to wrap my head around is for handles, there has to be somebody who knows some implementation of code which actually knows how to deal with that type of handle. Like if it's a file handle, so if I'm in a component that doesn't implement the file system, even if somebody gives me a handle that's for a file system, I don't have the code that can actually go and do those file system operations. So the only thing I can do is to basically make a call to the other component saying, here's the handle.
Well, okay, so yeah, the function binding is separate to the handle. So you got like the first layer is like if you've got a descriptor, and I take a descriptor as a handle, I'm gonna already have got to know about that descriptor, and I would have imported it from the home component that created that descriptor. So I know descriptor was created by this component. And so as soon as I get a handle to a descriptor, I already know that it comes, which component it comes from through the typing system. So I know whose code to call against the descriptor.
Right. Okay. So like that, I can see how you can say like here's a handle, but that's got to include, like you just said, the
type. Yeah.
Who can I pass this handle to? Right.
Yeah. And you can pass it to anyone, but the point is like if I get a handle to descriptor, I've got a local table that is tracking which descriptor I've got a handle to, and I'm managing that table and then if I pass it to another component, I'm looking up in my table, getting that pointer to the underlying descriptor, and then creating a handle in the other components table that's gonna have a pointer to the underlying descriptor, and I'm erasing my record and they're adding their record. So it's like it's all kind of track.
That I could understand, but the underlying descriptor, I guess at that level, you need to know this is a descriptor from
Yes, so
X.
resources are imported types, and you import it from a home component, so it has a home that it belongs to, and or it's your own, so you either
Right.
define the resource or someone else defines it and you import it from them, and then you wrap that in a handle.
Right.
And so there's a lot of handle tables, because if you've got 10 resources and 10 components, you're gonna have 100 tables, and that you're moving handles between. And so
Right.
part of the bind gen then becomes sharing tables, because now I need to do table modifications in the lower level bind gen. So it's complex, but it's as we expected roughly.
Definitely interesting. Is that last I see that's the optimized host one. That's the last one you
I
pasted.
showed that there, yeah. So yeah, this is something that I was able to just kind of push out. It's not something I can drive, and I don't have remaining resources to drive any low-level work, but I really wanted to get some low-level story together to kind of bridge all of these aspects. And so hopefully it's an outline of the problem space, I'm hoping, and demonstrates a kind of proof of concept and a cow path that in theory, you could imagine node native functions that implement all these things have a similar protocol for binding memory and tables and things. Obviously, when you can move fully into node, all the resource tables should be inside of node. You don't want to have user land resource tables, or if we have user land resource tables, you want them to be like first class constructible, like import resource table from WASI and then create a new one and then instantiate into the component. So maybe there's a high level language there. The scheme I came up with was like actually just sharing the slab data structure and then having conventions on top of that data structure, because that's a scheme that can work in user land without anything existing in native. And so as we think about what native involves, then obviously Jquery can adapt to that. Yeah, but the start of where a proposal might sit, I think.
Okay, well, it looks like we're just at the end of our time. It's certainly a lot of food for thought. Any other questions or discussion before we close out? Okay, well, thanks for your time and thanks for the update. Always learn stuff here, so that's
great to share. So,
okay, thanks. We'll see everybody in GitHub next time.
Thanks, everybody.